So today I'll be talking about some learning challenges in natural language processing. But before I start, I want to take a moment to appreciate where we are in NLP today. So as this audience knows more than any others, NLP today is all about contextualized representations. These are representations learned as a side effect of tasks such as large-scale machine translation and more commonly language modeling. We lovingly name these models after Sesame Street characters such as Bert and Elmo from here. The latest one is called Ernie, unless there has been a change in the last 1 week. Ernie does Chinese NLP. So as a field, we really, really like Sesame Street characters. So for the sake of completion, the way this works is we start with a large pre-trained language model. We run this language model on new data, optionally fine-tuning or not. The representations we get from this language model are then plugged into downstream tasks. And as a result, we see an improvement across the board over several different tasks. And this is pretty remarkable because we have taken an unsupervised method and used that to improve the performance of tasks that require supervision. So as a field, this is a pretty remarkable place to be in now. So let's look at a concrete example. This is an example of a reading comprehension task. As you know, you start with a passage and you are asked a question about the passage. And the task is to select some words in the passage, a continuous selection of words in the passage that might answer the question. So take a moment, read the passage, and see if you can answer the question, the number of new Huguenot colonists declined after what year? That's right. And our best models that use contextualized representations are able to answer that correctly. And this is pretty impressive because this passage is like non-trivial. There are lots of years in the passage. The sentence in which the answer occurs is fairly long and complicated. So this is very impressive. We have gotten to a point where our models are supposedly doing some amount of reasoning to get to the right answer. So that's very impressive. So how about we introduce a new sentence into the passage? What's the answer now?
1665. I mean, it thinks it's 1667.
Oh, wow, you're one step ahead of me. Yeah, that's right. This is what happens. And so this should give us pause for two different reasons. First, oh, shoot. Okay. Okay, I'm not going to use this clicker. All right, so this should give us pause for two different reasons, because the amount of reasoning we thought went into answering this question is clearly not happening, because that reasoning wouldn't have changed with the addition of this new sentence. So there is still something that our models do not have that is needed to answer these questions correctly. And the second reason is that this sentence that we introduced is called a distractor sentence. It looks very similar to the question. It's only different in a few words. And so this distractor sentence was able to confuse the model successfully. So maybe the model is relying on these shallow surface level patterns to reach to its answer without doing any reasoning. So this opens up the question of what exactly are our models using to get to the correct answer. So the two learning challenges I am going to look at is the first challenge is, can we incorporate some more prior information about language to improve our model performance? Here I will talk about work from EMNLP last year. And the second part, we will look at what is it in our data that is helping our models to get to their answers, maybe taking shortcuts without doing the actual reasoning. Here I will talk about work from NACL last year. All right. So digging a little deeper into that first question, can we incorporate some priors about language? So in this example, if you look at the sentence in which the answer occurs, there is a lot going on. There are 3 different events. A first batch of colonists arrives, and then a second batch of colonists arrives, and after that there is a decline in the number of colonists arriving. So within each event, there is some semantics of what's going on, who's arriving, when are they arriving, and the 3 events are connected together by some kind of a temporal relationship, which we need to understand. We need to understand each of the 3 parts individually, and we need to compose the meanings of each of the 3 parts to actually understand the meaning of the sentence. That means we need to look deeper into the structure of the sentence itself. So this kind of the prior knowledge that will help us understand this is linguistic structure. So the question now becomes, can linguistic structure act as the informative prior that is going to help us improve our models? So the particular kind of linguistic structure I want to consider in this talk is semantics. So semantics tells us who did what to whom. So let's look at a simpler sentence. After encouraging them, he told them goodbye and left for Macedonia. Even in this simpler sentence, there are 3 different things happening. There is an encouraging event, there is a telling event, and there is a leaving event. So these are the what's in the who did what to whom question. Now, if we look at each of these events separately, we'll see they have some individual structure. So we'll call these 3 events predicates. And if we look at the telling predicate, we'll see that there is a person who's doing the telling. We'll call that an argument 0. We see that there is the thing that is being told, that is argument 1. The recipient of the message is them, and that's argument 2. And finally, the telling is happening after encouraging them. So that is a temporal argument to the telling event. So these arguments tell us the who's and the whom's in the who did what to whom question. Similarly, we have the predicate argument structure for encouraging. Here it's much simpler. And finally, we have the predicate argument structure for leaving. So in this talk, I will be only looking at these kinds of predicate argument span-based semantics. Semantics is a very overloaded term in NLP, and it might mean a lot of different things, but we'll only be looking at these kinds of span-based semantics. And by span, I mean a continuous selection of text. So the question now becomes, can span-based semantics serve as the linguistic prior that is going to help us do better in our models? However, there's a problem here. Even though these structures look very intuitive, these kinds of predicate argument structures, they are surprisingly hard to predict. First of all, there is not enough data that we can train our models to predict these semantics, and as a result, the models themselves are still not quite there where we can use them to improve language understanding tasks. So we are going to take a step back and make our goal the prediction of these kinds of semantic structures from sentence, and to do that, we'll use a different kind of linguistic prior. Any questions? So luckily for us, we have a very good prior for semantics and syntax. So syntax you can think of as this foundation on which you can build these representations of meaning. So for the same sentence, this is what the phrase syntactic tree looks like. So all these phrases denote VP is verb phrase, NP is noun phrase, PP is prepositional phrase, and so on. And they all order up very neatly as a tree structure. And if you look at any particular node in the tree and you look at all its descendants at the leaf level, you will again get a span in the sentence. For example, the leftmost PP corresponds to the span after encouraging them. And this is good for us because we looked at semantic spans for the arguments and predicates. And so this is another representation that is going to yield similar spans. So knowing one kind of structure is going to help us know the semantic structures, which are also span-based. And it is no coincidence that these nodes actually correspond to spans. The annotations for the semantic predicates and arguments were actually made right on top of these syntactic nodes. So there is a one-to-one correspondence between syntax and semantics. So the idea is that, or the intuition is that, if we are able to predict the syntactic tree, or this kind of phrase syntactic tree, well, we might be able to use information from that tree in order to get to the semantic predicate argument structures, because they are very complementary. However, there is still a problem because as you can see, this tree is much more complex. It has much more going on than just the semantic parts that we are interested in. For example, there is all this verb phrase part of the tree here, which does not really correspond to the arguments at all. So, and everything needs to order up into a beautiful tree. But we don't care about that. We only care about only parts of the tree which correspond exactly to the semantic arguments and predicates we are interested in. And this intuition that we don't need the entire tree leads to the first work that we did at UMLP. This is joint work with Sam Thompson, Kenton Lee, Luke Zettelmeyer, and my advisor is Chris Dyer and Noah Smith. So the setting we are concerned with here is structured prediction with an auxiliary structure. And as we saw, this auxiliary structure is given by syntax. So the way we traditionally think about syntax as this auxiliary or this intermediate structure is we start from the input, which is a sentence typically. We predict the auxiliary structure for it, the syntactic tree. Using that auxiliary structure, we then go on to predict the primary structure of interest, which for us is span-based semantics. Now, since this forms some kind of a pipeline, and these kinds of pipelines have been around for a really long time. Typically, you repeat the same pipeline both at train and at test time. Now, one advantage of using this pipeline is that you have access to more structure. You can now use the syntactic tree to get to the semantic arguments. But at the same time, it also introduces this problem of cascading errors. That is, if you make a mistake in prediction of this auxiliary structure, which is syntax for us, there is no way you can overcome that mistake in predicting the primary structure. So there are advantages and disadvantages to using pipelines such as this. And one way to overcome these kinds of cascading errors is to use an end-to-end approach, where you go directly from the input to the primary structure, which is span-based semantics, without involving any syntax. Now, even though that has been shown to work very well, it has also been shown that if one was to incorporate syntax in these models, we would get even better performance. So we would be losing some amount of performance in giving up this intermediate auxiliary syntactic structure. So to give you a high-level overview of where our work fits into the large scheme of things, let's consider this plot. It's not an exact plot. It's just a cartoon plot for understanding where our approach fits into the large scheme of things. On the y-axis, we have the amount of syntax one would use at training time. And on the x-axis, we have the difficulty of designing and training these models. So we just saw that end-to-end modeling is syntax-free. You don't need to have access to any syntax during training. And we saw that syntactic pipelines have this problem of cascaded errors. You make an error in prediction of the syntax, and then that propagates to the next phase. Another alternative is to use a latent variable for syntax. So here, you don't have access to explicit syntax, or you don't need access to explicit syntax at train time. You just use syntax as a latent variable. And to get to the semantics, you marginalize over all possible variants of syntax and then predict the semantics. But remember, we saw that the tree structure that corresponds to a sentence can be very complicated. So as a result, we'll be spending a lot of time marginalizing over all possible tree structures for that sentence. So there are both advantages and disadvantages of using these kinds of latent variable models, and they can be expensive too. Another approach is to jointly model both syntax and semantics. So for the given same sentence, you would predict both the syntactic tree and the semantic graph. Now, so from the point of view of the model, you are doing a single task. You have a single objective, a joint objective for predicting both kinds of structures. So these kinds of models tend to work well, but because the inference problem is complicated, you're predicting both these kinds of structures at the same time. They can not work as well as, say, pipelines. So one simplification of this is multitask parameter sharing, where from the point of view of the model now, you have two different objectives, one for syntax and one for semantics. So you will be optimizing both objectives at the same time, and you will be sharing some parameters between the two objectives, but each of these two tasks will get their task-specific parameters. Now, this works well, but you have to still do each task separately. Like, you have to predict that entire syntactic tree and the entire semantic graph. And as we saw, we do not really need to predict the entire syntactic tree to get to the semantic graph, because that's what we are interested in. So we will be using a further simplification of this multitask approach in syntactic scaffolds. Yeah, so it's simpler than the multitask parameter sharing approach in that we are not predicting the entire tree, but we are still in the same multitask regime. So to be a little more concrete, we're still in the multitask setting where, given the input, our primary task is the span-based semantics tasks. So here we have 3 different flavors of span-based semantic structures. I won't go into the details of each of the structures, but you can think of them as 3 different span-based semantic formalisms. And as our scaffold task, we have syntax. And here I have task in quotes because we're not really predicting the full syntactic tree. Instead, we'll be predicting very, very shallow syntactic representations. So now we will be learning a very soft notion of syntax in the representations for the sentence. And because this is a soft notion, we won't be in this zone of making cascaded errors. So we will just be learning representations which are aware of the syntax and are not conditioning on any hard intermediate syntax. And because this is a representation learning approach, we can discard this part of the network at test time, and we only need to worry about training the scaffold at train time. Okay, so now the question is, what defines the shallow syntax that we would be interested in? So one simple way of looking at things is just ignoring parts of the tree which do not, or nodes in the tree which do not exactly correspond to predicates and arguments. Or in our case, because we will assume that we have access to predicates and we are just predicting the arguments, we will discard all parts of the tree that do not exactly correspond to arguments. And so the modified tree looks, or tree-like structure, or partial tree looks somewhat like this. So the task boils down to the following. For every span in the sentence, we are going to predict whether or not the span corresponds to a phrase type which has a one-to-one correspondence to any argument type. Now, in this example, as you can see, all the arguments correspond to either prepositional phrases or noun phrases. So the task that we can think of is to predict for every span in the sentence whether or not it would correspond to a prepositional phrase or a noun phrase in its syntactic tree. Any questions? I guess you all know this paper. This is an AI2 paper. Yeah. So one question here is that if we are considering every span in the sentence, this could be a quadratic time problem. But for simplicity, we actually discard all the spans which are longer than a certain length d, which typically in this task corresponds to 15 tokens.
Do you make the classification only for the legitimate spans?
We make the classification for all spans.
So it should learn to recognize a span that's not span.
Yeah, exactly. But still, if we want to, we also want to discard certain spans which will not even be semantic arguments. So semantic arguments are typically not so long. So we still want to prune out unnecessary spans. Yep. All right, so to be a little more concrete, this objective looks at the sentence X and Z, which is a set of all the spans in the sentence which correspond to a particular phrase type. Note here that most spans in the sentence will correspond to the null phrase because most spans won't be phrases in the sentence. So, and we are predicting for each span its phrase type. All right, so training with syntactic scaffolds is pretty straightforward. We just saw the scaffold objective, and we have the primary task objective, which I haven't talked about at all so far. And all we do is interpolate these two objectives using a mixing ratio delta. So here again, X is the input sentence, Y is the primary task, which is the span predicate argument structures, and Z is the scaffold structure. For us, it is just spans corresponding to certain phrase types. And we just need to optimize this objective. Now, one thing here that you may note that in the first objective, we have D1 as the primary data set. And in the second objective, D2 is the scaffold data set. These need not be the same data sets, which means to say that you can have all your syntactic annotations on an entirely different data set. You can train your objective, the scaffold objective, on that data set. And you can think of this as some kind of a pre-training in that case. Like if you had access to unlimited amounts of syntax, you would train this scaffold, use the representations that you learn on that data set, and plug it into the primary task of interest. So one thing that's common in the two objectives are these shared parameters theta, which correspond to input level parameters. And each task gets its own task-specific parameters, phi and psi, respectively. All right, so I haven't talked about the primary objective so far. This objective corresponds to prediction of the span-based semantics. So here the only consideration we will look at is that we need to score the same structures. To make the most of this kind of a multitask setting we have, we should be scoring the same structures in both tasks, the primary and the scaffold task. And in our case, because the primary task that we are interested in is span-based semantics, we should be scoring the same spans in the primary as well as scaffold task. So one option for the primary test then is a span-based classification objective, much like the scaffold objective with GISSUM, with some aggressive pruning to get rid of spans which are most likely not going to be the arguments that we are interested in. And we do this for the co-reference resolution task, which is one of the tasks we consider here. Another option is a semi-Markov conditional random field, which I'll go into a little more detail. So remember, the task that we are interested in is given a sentence and a particular predicate. We want to predict these argument structures. So this can be considered a segmentation, where some words in the sentence do not correspond to any argument. So we'll, in practice, use a null argument to represent these words. So we have to figure out a segmentation for the sentence which corresponds to these argument structures. So a semi-Markov CRF is a generalization of a CRF. You're still scoring an entire segmentation given the sentence. But instead of modeling each position at a time, one position at a time, you're modeling both the label and the length of each segment. So at every time step, we are trying to decide what constitutes an input segment as well as label that segment at the same time. So here by a segment, I mean the indices of the begin and end position of the span and the label corresponding to that span. And the score of the entire segmentation is the sum of individual segments. And here, training and inference can be given by dynamic programs. The complexity here is O of NDL. N is the length of the sentence. D is the maximum length of the spans we want to consider. And L is the number of labels. These are semantic labels here. And we use a 0th order Markovian assumption because we are already scoring spans, so we have some amount of information about contiguous positions. I mean, you could use a higher order Markovian assumption, but that would make things way more expensive. All right, so now let's look at the model architecture. So for the same sentence that we used, we first start with the word embeddings for that sentence. Here, the word said corresponds to the predicate we are concerned with. So it will get a special embedding to indicate that this is indeed a predicate position. We pass these word embeddings through a bidirectional LSTM. To construct the span embeddings, we'll just use the hidden representations of the begin, the start position and the end position of the span. Now, because we have some amount of contextualization that comes with using the bidirectional LSTM, these will be representations of the span and context. Now, to incorporate some more information about the span, we will add an intra-span attention. This attention mechanism looks at every word in the span and computes a weighted average of all the hidden representations for the internal words in the span. And we then concatenate this weighted average to the span embedding that we constructed by concatenating the first and the last word in the span. Now, here I've only shown 5 spans, but in practice, we'll have to do this for all possible spans in the sentence. Now, once we have computed the span embedding, we can either compute a scaffold score. So we'll pass this span embedding through a multi-layer perceptron to get a scaffold score when we have annotations for syntax. The same span embedding can be plugged into a different multi-layer perceptron to get a semantic score when we have semantic annotations. So here, the trick is that you only need to train the particular, or you only need to compute the particular score when you have the annotations for it. You don't need to do both at the same time. All right, so moving on to some results. For the first task, it's a frame semantic role labeling tasks, the similar kinds of predicate argument structures we saw, just a little more fine-grained. We see that the semi-CRF baseline already improves over prior state of the art at the time, and the scaffold task gets a further improvement over it. For a different kind of semantic role labeling task, which is ProbBank, which is exactly the formalism we saw in the examples, we see a similar trend. This semi-CRF baseline improves prior state of the art, but here the degree of the improvement of the scaffold is much lesser. And so one reason for this is that in the second task, there is a full overlap between the scaffold and the primary datasets. So some of the advantage that the frame SRL task is getting is probably access to much more data. But still, even if there is a full overlap between the scaffold and the primary dataset, we see there is some amount of improvement. And for co-reference resolution, it is exactly the same case. There is a full overlap between the in the onto notes data set, which has annotations for both co-reference as well as syntax, but we still get an improvement. Questions?
So when you, in the earlier example, when you were discussing all the things that go into the scaffolding, a lot of those were MPs.
Mm-hmm.
So
Yeah.
can you do, or did you do manipulations here where you sort of like remove just that particular class?
Yes. Yeah, so it's an empirical question, like what forms the best scaffold? And we played around with a lot of different kinds of scaffolds. So the NPPP scaffold works best for these kinds of SRL tasks. For co-reference, most entities are not prepositional phrase, they are mostly noun phrases, so that works best. But we experimented with different kinds of scaffolds, like there was a 0-1 scaffold, where for every span we predicted whether or not it is any phrase type. And then we had for every span predicting the actual phrase type, and so on. And this worked best. Yes?
Comparisons, I remember earlier on when we were motivating it, you compared with Scribble at
Mm-hmm.
where they did the full multitask. Seems like that's more direct.
Yeah, sorry.
No, it seems like that's like the one I would be curious to see.
Yeah, so they don't report. So SRL has like all these different settings. They don't exactly report the same setting as us. So on a similar setting where they use a different kind of predicates, they get 83.4, which is close to what we are getting. So it's in the same ballpark, but it's not exactly comparable because, yeah, they do not report results on that. Yeah, I did talk to them about this very recently. Yeah, so one question I get here is, what about contextualized representations? So, so these are the results on the frame SRL task with and without Elmo. As we saw, without Elmo, there was like a big difference, but that difference reduces quite a bit when we use Elmo. So this shows that a lot of the gain still comes from having access to much more data. But there is still some amount of gain that comes from having access to these kinds of syntactic structures also. So it's not completely out of date. All right, so to recap this part, the learning challenge we wanted to solve was, can linguistic structure act as one kind of informative prior to improve our models? The task we considered here was semantic predicate or span-based semantic tasks. For this, we used phrase syntactic trees as our prior linguistic prior. We used a method which is a further simplification of the multitask setting, and we saw improvements across 3 different tasks. Yeah, here I have the Struble et al. Results, Kyle. Yeah, so I clarified with them, and apparently there was like a difference in settings, so it's not exactly comparable, so I removed that, but I forgot to do that here. But yeah, it's in the same ballpark-ish. Yeah. More questions? Yes.
Which data set did you use for your phrase syntactic?
Yeah, we use onto notes, syntax from onto notes, which is, yeah.
Would it matter which data set you use?
Not really, as long as they are, gold syntactic. In fact, it could also be predicted syntax, right? Like you could take the 1 billion word corpus, predict syntactic trees on it, train a scaffold on it, and plug it in. So that would also work. Only the problem is that when we use predicted syntax on a different domain, the quality reduces dramatically. So there's a risk in doing that. All right. So what next? So in this work, we showed how to get from the sentence to its semantic structure. And to do that, we use syntax as this intermediate. But remember, we had this original reading comprehension style tasks that we are mostly interested in. So there's nothing to prevent this pipeline from happening. We can use predicted syntactic or goal syntactic structure as a scaffold, and even semantic structure as a scaffold to get to better representations that help us in reading comprehension style downstream tasks. So essentially what we want to do is representation learning using different kinds of structural representations for the sentences. And recently I've been thinking about that these representations need not just be about a particular sentence itself. They can be broader knowledge graph style representations which span over different kinds of sentences, as long as there is some mapping between these unstructured sentences and some kind of structure. It is possible to do representation learning with both these kinds of inputs. A different kind of application is we can start with the input sentence and its syntactic and semantic structure. We can modify the syntactic structure in a very controlled fashion to get to a transformed input such that the semantics of the input doesn't change. So this corresponds to paraphrase generation, and work has been done in along these lines, but they do not take into account the semantic graph of the sentence, which we could take into account and hold that as a constraint that it needs to satisfy to get from the input to the transformed input by modifying just the syntax such that the semantics stays constant. An even more interesting application is it possible to alter the semantics, again, in very controlled ways, so we can transfer some attributes between the original input sentence and the transformed input. So this is also a case of control generation, and I'm very interested in applications such as this. All right, I'll be switching gears a little bit before going into part 2, but ask questions if you have any. All right, so going back to the original example we had, we saw that introduction of a sentence which looks very much like the question confused the model successfully. And here the question we wanted to ask is, are there things in the data that are causing our models to make their predictions either correctly or incorrectly? And here I'll talk about work on annotation artifacts. This is joint work with Sachin, Roy, and Noah here, and Omar at UW and now at FAIR, and Sam Bowman from NYU. So the task here is natural language inference. So given a premise, the task is to predict whether a hypothesis is true, false, or neither. So as an example, we have a premise: 2 dogs are running through a field. And if we have a hypothesis, the pets are sitting on a couch, we have to predict whether this hypothesis entails the premise, which means that is the hypothesis true given the premise? Does it contradict the premise, or is it not possible to say whether or not it is true or false given the premise? So what do you think the answer is? Roy doesn't get to answer this. Yeah, it's a contradiction. So it's very straightforward. Yeah, so unlike the previous setting that we saw where data was a limitation, in this case we have a lot more data. And the reason we have large data sets is because of the process the data sets were created. So these premises were extracted from captions from the Flickr dataset for the Stanford NLI task. These were shown to annotators on a crowdsourcing platform. The annotators were then asked to generate 3 different sentences or 3 different hypotheses, one that entails the premise, one that is neutral to the premise, and one that contradicts the premise. And because these annotators were doing these kinds of tasks very fast, you get hundreds of thousands of examples in each of these data sets. And so these data sets, because there's so much data and they are, it's an interesting task. It's a simple classification task. Lots of progress has been made on this task since it was introduced. So it came out like 2 years ago, and performance has gone up by like 20 points. And I don't think this even includes the latest BERT results. There are some Elmo variations in these results. So the way this task is treated, it's generally treated as a pairwise text classification task. So the premise and the hypotheses are encoded separately, and then they are passed through a network that does some amount of that uses some amount of intra-sentence and inter-sentence attention to get to the final classification task, whether or not the premise entails or is neutral or contradicts the whether or not the hypothesis has these relations with the premise. So we tried this simple experiment where we just replaced the premise in this task with a degenerate null string. So we wanted to see what kinds of baselines were good for this task. And we did this very simple experiment, just playing around. And to see what this model learns, the task is actually given no premise. Is a hypothesis true, false, or neither? So as an example, you're given a hypothesis. The little boy is diving off the diving board because he's an excellent swimmer. And the task is to predict true, false, or cannot say. What do you think the answer is? Even that doesn't make sense because we don't have a premise that it is neutral to. So this is a totally nonsensical task. But to our surprise, we got very, very good results on this task. The performance of our models were much higher than the majority class baseline. As this work came out, 2 other groups also had similar results. So this was all very, very surprising to us. So the first thing we tried after this is we wanted to fix this data set. So the first thing we tried is can we use our simple baseline to to divide the data into 2 parts. One that is easy, which has been solved by this simple baseline, and the examples that we are still not able to get were actually the NLI examples, which were the hard examples. So this was our first variant of the experiments we tried. So not surprisingly, we saw that on the easy examples, the performance of state-of-the-art models was very high, whereas the model struggled with the hard examples. So this was kind of expected. So at this point, we came to the conclusion that maybe NLI is not yet solved, and it is possible that these models are just using these easy examples to inflate their performance, and we were still very, very hopeful that we can fix this. So one way to go about fixing it is we started looking at the different classes. So for all the easy examples, that is the examples we got right, we started looking at the examples themselves. So for the entailment class, the kinds of patterns we saw were generalization. So the premise, words in the premise such as some men and boys becomes people. So that's a general way of saying some men and boys. Grassy area becomes outdoors. So that's also a general way. In case of the neutral examples, it's the opposite trend. Here we add more information into the neutral hypothesis. So a train becomes a black Amtrak train, which kind of modifies the sentence in ways which you may or may not be able to tell. So whenever you see these kinds of modifiers, lots of adjectives, it was a good indicator that it could be a neutral sentence. And finally, for contradiction, we saw examples that had these trivial ways of introducing contradictions, like dogs became cats in the hypothesis. So whenever the model sees something like cats, it thinks it's a contradiction. Yeah, so one reason we think these kinds of artifacts came into being is that the annotators from the crowdsourcing platform were most likely optimizing for the number of examples that they could generate in a given amount of time. And that's totally fair. If I was a crowdsource annotator, I would try to maximize my rewards that way. But as in the process, what they did is that they took the seed examples. I think this is an example from that was provided to them. And as you can see, these also have the kind of artifacts that I mentioned. So 2 dogs becomes animals. Running through a field, 2 catch a stick. So that's like more information that is not necessarily true. So they took these seed examples and used heuristics, either consciously or unconsciously, to create these hypotheses, which kind of made the task much easier. So yeah, so at this point, we are still very hopeful that we can fix this. But at this point, we started noticing certain things. First of all, we noticed that the hard examples exhibit their own artifacts. So for example, the neutral class in the hard subset contained a lot of negations. And negations is a property of contradictions. And in our easy examples, we were able to filter out a lot of the contradictions which contained negation words. But in the hard examples, we saw a lot of neutral class hypotheses which contained negations. So maybe we could train another classifier on top of the hard examples to filter this out, and then we can filter out again. But there's no easy way to filter out all these artifacts once they are baked into the data set. So, and another reason is that the artifacts that we filtered out were still very valid examples of inference, like negations are contradictions, and there is nothing to say that these models should not learn these simple kinds of inference examples. So the bottom line is, once a data set is created in a certain way, it's very hard to filter out the artifacts to make like a harder or a cleaner data set. So what do we do next? So let's just assume that we have a lot of these data sets with artifacts. What can we do next? So the intuition here is that the models which exploit artifacts could be repurposed as models which can detect these artifacts. And to do that, we could use stylistic global features such as length of the sentence and word usage and so on. Now, once we have these kinds of artifact detecting models, maybe we can, instead of treating every sample in the data set equally, we could treat samples differently based on how easy or hard they could be. So instead of assigning them these 0, 1 labels, we could assign them some kinds of weights to show how representative of the phenomena they're trying to capture they are. So this is something I am interested in, to encounter data sets with artifacts. Another direction that people have started exploring is improved data collection. So one thing that people have come up with, and 2 of these data sets are from AI2, is they have these partial input baselines. So while they're constructing the data, they take into account that there could be samples which make the task trivially solvable. So they come up with these partial input baselines, or in the case of SWAG, like a mechanism to filter out all these trivially solvable examples as the data set is being constructed. So that's a positive outcome of this. A second outcome, which is a little non-typical, is can we come up with alternatives for building these kinds of inference data sets which do not take into account any human involvement. There doesn't have to be an annotator that's sitting and generating these data sets. And this ties into the work or the direction I previously pointed out, where we can take an input sentence, its linguistic structure, and try to transform that input by making systematic or control changes to the input structure. So this would correspond to some kind of attribute or style transfer, but instead of transferring attributes, we would be transferring the kind of relationships between the premise and the hypothesis. So yeah, I'm interested in these kinds of tasks which could get rid of this annotator in the loop, but maybe we can add back the annotators to filter out a lot of the noisy examples one could generate by a process like this. All right, so I'm concluding my talk here. It's an exciting time for NLP. So it looks like we have arrived, and New York Times is noticing us, and yeah, our parents and our grandparents know what we are working on. So that's a good time for us to be in. But we do have certain outstanding learning challenges still. We need to figure out how to incorporate more information to improve our model performance, as well as we need to build models which could be robust to certain kinds of artifacts that are in our data sets. So that's all I have here. Thanks.